Hello students, today we are going to see some more interesting and important questions from MS Chouhan sir's Organic Chemistry level 1 and the question from 121 to 130. Come on, let us discuss the first question. Total number of stereoisomers formed by the given compound. So as you are looking at this compound, this is trimethyl cyclohexane, that is 135 trimethyl cyclohexane. In that, how many chiral center is available? Do you think there is a chiral center? Chiral center means 4 different groups or atoms attached to that carbon. That is called chiral carbon. But here, as you are checking here 1, that means here and here both are same. And the same way here, if you are checking here and here, that is CH2, CH2, both are same. And the same way here also, this side and this side. So this also sends it means there is no chiral carbon. That means total number of stereoisomers they are asking. Okay, yes, is it possible? Yes, of course it is possible. Come on, let us check with that. So if suppose this is cyclohexane, in that one, it is 1 point, it might be like, what is it, wedge point. The other position, I just draw, you just remember that. So the other position, one side it is a dash, the other side it's a wedge. So in this way, so when you cut over here, so this is actually, what do you feel, what do you see to that? This is POS is present. And this side, when you cut over here, this side also POS is present. So POS is present means this is achiral, right? So this is what it is, achiral, both. Now when you're looking at this cis and trans, can we bring it both? Can we bring cis and trans? This is a wedge position and this is a wedge and a dash. So in this way we can identify what it is, wedge and dash. So we can bring it to stereomers, that is cis and trans. Can we bring it in this way? Yes, cis and trans. This is the same side, it is cis and trans. Like see, this is trans, and the same way this side also, this is trans and this is cis, right? So this is cis and this is trans. And the same way this side also you are finding that is a cis. This is cis and this is trans, right? Okay, hope you got the clarity. So that means how many isomers, that means stereoisomers formed, total number of stereoisomers, that is only 2. Hope you got the clarity. How do we bring this point over in discussion? Come on, let's go to the next question. Number of stereoisomers formed by the given compound. Yes, come on, let us check how many stereomers are possible. Now here cyclohexane, this is cyclohexane. In that nitrogen is present here. In this point nitrogen is present, and here also nitrogen is present, and then hydrogen which is attached over here both the side, and this side double bond O and opposite side also double bond O. This side CH3, right? This side CH3 is there, no? So I just put it in this both the side wedge position CH3, right? And the next same idea, I just bring it here. Here cyclohexane, both I'll draw totally, then I will explain to you. So this is hydrogen and this side also hydrogen. In that one side it is a dash position CH3, the other side wedge position CH3, right? And this is a double bond O and this side double bond O. Okay, now in this point, so as you're looking at that, here in this point there is a chiral carbon, is available chiral carbon, because chiral carbon means what it is, 4 different groups or atoms attached to that carbon, that is called chiral carbon. So that means here CH3, here C double bond O, here NH, and this side one more hydrogen is available. So that definitely this is a chiral carbon, and this side also chiral carbon, same as it is. So that means, do you think it is POS is available? No, POS is absent and COS also absent. So POS COS absent means 100% it is chiral. So chiral it is present means, can we identify absolute configuration, that is RS configuration? So definitely MI, what is it, MI, mirror image also it is possible. So non-superimposable mirror images, that is enantiomers. Enantiomers is possible in this point? Yes, it is possible. Enantiomers, it is possible. So in this compound, you will get that opposite of this side. Okay, now in that enantiomers, so enantiomers means 2 will be available, this one and opposite one, non-superimposable mirror image. And the next one, meso, you can identify. How do we identify meso? Meso, minimum 2 chiral center it has to be present. Yes, 2 chiral center. And the next one, here when you cut over here, what do you observe? Here you can observe what it is, COS is present. So COS is present and at minimum 2 chiral center it is available, means here 100% this is what it is, meso is present. Okay, so that means this is 2 and this is 1, only 1 meso it is available, right? So that means what it is, this is superimposable mirror images, optically inactive, and this is optically active. Hope you got the clarity. So meso it is optically inactive, remember, meso it is optically inactive, and this is optically active. Why it is? POS CO is absent, chiral and non-superimposable mirror image, 100% it is optically active. So totally 2 plus 1, 3 stereomers is possible. So how many stereoisomers are possible? That is 3 stereoisomers are possible. Yes, 3 stereoisomers. Hope you got the clarity. Come on, let's go to the next question. Which of the following compound does not undergo base catalyzed exchange of D2O, deuterium oxide, even though it has an alpha hydrogen? So this question basically it is tautomerization, that is ketoenol tautomerism, right? So in that specially what it is, alpha hydrogen it is there, that means it is possible for tautomerization, that you know very well. But in that which does not undergo tautomerization, that is what the question it is. See now in that option A here, what it is keto group, here also keto group, in this alpha hydrogen is available. So alpha hydrogen is there means that side, this side also it's available. So what happened, this transfer the electron and at resonance takes place. So naturally what happened, alpha hydrogen is there and what it is, tautomerization takes place. But the question what it is does not undergo tautomerization. So that means here also alpha hydrogen is available, in this point here also alpha hydrogen is there next to that adjacent carbon of keto group. Yes, so that means do you think it will transfer the electrons? Yes, it will take the transfer of electron. So what happened, double bond takes place over here. So the double bond takes place over here and here also double bond takes place over there. So in these two compounds actually bridgehead carbon is available. So bridgehead carbon do not have double bond because it will be unstable. So bridgehead carbon do not have what it is, double bond, right? So it is actually why it is unstable. You know what is that rule? It's a Bridgehead rule. Okay, so this is actually Bridge rule. Bridge rule. So Bridgehead carbon do not have double bond. If it is double bond is possible, it is unstable. So 100% this is unstable. So these are the two main compound does not undergo what it is, tautomerization with exchange of D2O. So that means B and C both are correct actually, which is the correct option, B and C. I hope you got the clarity why B and C does not go tautomerization, because it is bridgehead carbon double bond is possible means it is unstable, that is Bridge rule. Hope you got the clarity. Come on, let's go to the next question. Identify the product formed in the above reaction. The same idea, ketoenol tautomerism only. So the four main points can favor that what it is, ketoenol tautomerism. The first one, it is aromaticity. So the first one, what do we can give that point? It is aromaticity. Okay, so why that aromaticity we are giving that importance? Because a resonance will be there, a resonance. Right, now second one, what it is? Intramolecular hydrogen bond. Molecular hydrogen bonding. Why? You know, it will be very stronger because it will be within the molecules. Now third one, what it is? AMG. What it is AMG? Active methylene group. We can bring it that point. Active methylene group. Right, so active methylene group actually here, what is it? Active methylene group important. It is acidic hydrogen is available. So acidic hydrogen is available. So it is ready to donate that hydrogen. So these are all favors what it is, tautomization. Okay, now in that, so D2O which is reacting, so D2O which is reacting means what is the compound you can identify. So in this compound you will get what it is here, alpha hydrogen, where that alpha hydrogen will be available. In this point you can identify alpha hydrogen, so that means D2O, no, so D will be available. In this point D will be available because active methylene group, you know what is it, active methylene group to keto group, in between this is called active methylene group. And the next one which is acidic hydrogen is present, so that is also can be replaceable. So in this hydrogen which is acting as an acidic hydrogen, so this also can be replaced to OD. And then this point which is available here next to this point also OD. So that means this point which is possible for this point, so here I just mentioned here, in this point you can bring it OD, and this point here also you can bring it, and this point and this point. Okay, so these are the 4 points which is possible. Come on, let us check with that answer. So option A, B, C, D. Right now here this point it is possible, D and D, this point also because active methylene group, and this point also acidic hydrogen, and this point also can be replaceable acidic hydrogen. So these are all the points. So option B is the correct. Hope you got the clarity. Now that same thing what I have drawn over here, the compound has come here. I hope you got the clarity. So which is the correct option? Option B is the correct option. I hope you got the clarity. These are the main points favors that ketoenol tautomerism. Aromaticity, that is resonance point will be available, and intramolecular hydrogen bonding, that is very strong bond and it will be more stable. And AMG, active methylene group, wherever active methylene group, that is acidic hydrogen is present, so acidic hydrogen ready to donate, so that you will get what it is, enol formation. Hope you got the clarity. Come on, let's go to the next question. And in 3-methyl 2-cyclohexanone, which hydrogen cannot undergo deuterium exchange when it is reacts with CH3O minus. So CH3O minus, which hydrogen, that is hydrogen 1, 2, 3, 4, 5 it has given. So in that 3-methyl 2-cyclohexanone, right now in that which hydrogen cannot undergo what it is, deuterium exchange. So it is actually here they have given CH3 O minus. So that means here minus is available, means due to that what it is, resonance. So this will transfer to here. So this will transfer over here means automatically what happened? This one will transfer over here, and then this one will transfer over here. Right now, that means this point and H5 it is alpha hydrogen, and of course due to the resonance from here, one it is possible CH3 it is hydrogen. CH2 and H it is there, that is hydrogen 2. This also it is possible for replacing, exchanging, and H3 this also it is possible. So alpha hydrogen 100% it is possible because next to that keto group alpha hydrogen is. So that means H1 it is possible, H2 it is possible, H3 it is possible, H5 it is possible. That means they are asking the question that hydrogen which cannot undergo deuterium exchange. So that means H4 cannot undergo. Why? Because this from here and here to there it is resonance, it will be taking place. And one more thing, this also can be replaceable. Why? Because it is alpha hydrogen. But in this point there is no point to exchange. So H4 does not undergo deuterium exchange. Hope you got the clarity. So that means which is the correct option? Option B is the correct option. H4 cannot undergo deuterium exchange. Hope you got the clarity why I've given that answer H4. Why can't other things it is possible? Like why these are all possible for exchange of deuterium, where H4 it is not possible. I hope you got the clarity. The simple reason, a resonance, suppose if it is present CH3, so here minus automatically transferring that electrons, and due to that resonance it goes, right? Hope you got the clarity. Come on, let's go to the next question. I have given compound 1 2 3. In that tautomer of 2, tautomer of 2 which is eligible for tautomer of 2, they are asking. That means which can bring that tautomer 2. Okay, now in this point here hydrogen, alpha hydrogen is available, right? So alpha hydrogen is available because keto group it is there next to that alpha hydrogen. So definitely this will transfer that electron, and when it is transferred the electron due to conjugation resonance, so naturally you will get the double bond over here. When you're getting double bond, what it does here, yes, double bond, and here OH will be there because this hydrogen shift. So automatically this compound 1 can possible, that means it is eligible for what it is, tautomer of 2. Yes, this is possible. Compound 1 it is possible, and compound 3 let us check. So compound 3 here also 2 hydrogen it is available. So 2 hydrogen is available means here it will transfer. So due to that conjugation what happened, this also will be taking place, resonance. So naturally hydrogen shift, so that means here what it is, OH it is possible. Yes, that means compound 3 also it is eligible to be as a tautomer of second. So both 1 and 3 it is possible for the tautomer of 2. So that means which is the correct option? Option C, both 1 and 3 it is eligible for the tautomer of 2. I hope you got the clarity. So tautomer, that keto enol tautomerization, the same idea, I just bring it to your notice. So the first one atomicity, that is resonance, and the second one intramolecular hydrogen bonding, third one what it is, active methylene group. So these are the main points that you have to remember when you're going for keto enol tautomerization, which can be replaceable, which cannot be replaceable. In these 3-4 points only you are getting to that. So conjugation also in another one more point. Yes, come on, let's go to the next point. In the ionization of the given molecule, the hydrogen atom involved, that is alpha hydrogen, beta hydrogen, gamma hydrogen. So this is keto group, and here double bond is there both the side like a pillars. Now in this point, which hydrogen atom, alpha, beta, gamma, which is possible, which is eligible to go for that ionization? That is what the question. Now here one more point I wanted to bring, as I mentioned, that rule of aromaticity, resonance, intramolecular hydrogen bonding, and active methylene group, all these points added to that sp3 hydrogen, that is actually here I just mentioned sp3 hybridization of hydrogen, which is possible for that ionization, that is actually acceptable for that what it is, acidic hydrogen. Whereas sp2 hydrogen, which is not possible for ionization, whereas sp3 it gives what it is, acidic hydrogen, that is alpha hydrogen. So that means here 2 hydrogen will be available, here 1 hydrogen, here 1 hydrogen, whereas here what it is, only 1 hydrogen which is possible. So this is not possible to go for that ionization, whereas here alpha hydrogen is there, no? So this point it is minus charge, so minus charge it will be transferred over here and conjugation takes place, and here definitely what it is, resonance will be available. So naturally this point which is going for that, this is eligible to go and form as a enol formation. Right now in that enolization of the given molecule, H hydrogen atom involved, gamma hydrogen is having that eligibility to go and form as a enolization, whereas hydrogen alpha, hydrogen beta, which is not possible. Why? Because actually these are sp2 hydrogen it is formed. Hope you got the clarity. Come on, let's go to the next question. Point, among the given structure which can exhibit tautomerization, that is tautomerism. Okay, in this point here sp2, both the side sp2 carbonate is available. Of course keto group is there, and there is no alpha hydrogen. Actually in this point you can identify only sp2 only it is available. So sp2 carbon which is not applicable for tautomerization. Why? Because there is no alpha hydrogen is not there. So alpha hydrogen actually replacing that what it is, OH. So that means here in this point acidic hydrogen is not possible to get that tautomerization. That means enol formation, which you cannot bring it. So, and as we are observing here also, you cannot get that what it is tautomerization, because sp2 hybridization. So sp2 hybridization hydrogen, which cannot replaceable, that means tautomerization which is not possible when sp2 carbon is available, which cannot provide acidic hydrogen. So naturally, what it is, compound 1 and compound 3 does not participate, that means it cannot provide that acidic hydrogen. Why? Because it is having sp2 hybridization. Where sp3 hybridization is there, means that can provide acidic hydrogen, that means alpha hydrogen is available. Alpha hydrogen can provide acidic hydrogen. Acidic hydrogen can be replaceable for enol formation. So where can we identify that enol formation? Now in this point here, hydrogen is available, here also hydrogen is available. So in that way, what it is, this can give that enol formation. And this point also, so here sp3 hybridization is available. So sp3 carbon can provide alpha hydrogen. Alpha hydrogen can provide acidic hydrogen. Right, I hope you got the clarity. And one more point also I wanted to mention here, AMG. What do you mean by AMG? AMG means here active methylene group. Active methylene group, it is ready to provide that acidic hydrogen. That is what indirectly I just mentioned. sp3 hydrogen, sp3 carbon can provide that hydrogen, that is acidic hydrogen. So all these formats for enolization, please remember all the points. Again, I'm repeating so that it will be really helpful for you. So the first one, aromaticity, that is resonance. The second one, intramolecular hydrogen bonding. And the third one, active methylene group. Yes, this is also active methylene group only. This point, alpha hydrogen, one more thing. Right, so these are all the points are applicable. And here now we got that idea, sp3 carbon is having alpha hydrogen, that can provide acidic hydrogen. Hope you got the clarity. Now which is the correct option, first, second, or third? Second only it is possible, so only second is the correct option. Hope you got the clarity. Come on, let's go to the next question. Identify which can exhibit tautomerization, that is tautomerism. Okay, now in this point I just mentioned here, do you find any double bond over there in the ring? No, it is not, we cannot find it. Now wherever keto group it is there, next to that adjacent carbon is having alpha hydrogen. So this is actually alpha hydrogen only, it is available. So in this point alpha hydrogen is present, and then this point also alpha hydrogen, this point it is alpha hydrogen is present, and this point also alpha hydrogen, that is active methylene group, 100% alpha hydrogen is available. So definitely you can identify here enolization, it is possible. So usually acidic hydrogen, where do we identify acidic hydrogen? Usually you can identify in that adjacent carbon attached to that carbonyl group, adjacent carbon which is attached to that carbonyl group, allowing that conversion between keto enol tautomerization. So keto enol tautomerization, just remember aldehyde and ketone can exhibit tautomerization. Right now, remember all those points, whichever I just mentioned, those important points to be noted down in that aromaticity, intramolecular hydrogen bonding, and active methylene group, sp3 carbon. These are all possible for tautomerization. In that amount, which is the correct option? All these are possible for tautomerization. Right, so which is the correct option? This also it is possible for tautomerism, this also it's possible for tautomerism, and this also it's possible for tautomerism. Why? Because alpha hydrogen is there to provide that acidic hydrogen, so you can find that enolization form. Right, so which is the correct option? Option D is the correct option. I hope you got the clarity. Come on, H double bond O reversible, CH2 double bond CHOH. Here between these two tautomers, which is more stable, they are asking. Okay, I just mentioned over here in this point, CH3 C double bond O, here H, actually it looks like it is aldehyde only. Here CH2, right, here it has mentioned CH2 double bond CH, here OH. So in this point I wanted to mention here, in this here actually CH2, here I just mentioned CH2, here one hydrogen. So what happened, this hydrogen transfers, that means the electron transfers over here. Now this point, and the same way, that is what CH2 double bond CH, that hydrogen shift takes place in that keto group. Why I just mentioned over here, keto group is more stronger than enol point. Why? Bond energy, higher bond energy, you can identify C double bond O, that is carbonyl group, it is more stronger, that means it is more stable. Higher bond energy, thermodynamically more stable. Higher bond energy, thermodynamically more stable. Right, thermodynamically more stable, you can identify in carbonyl group. So here I just wanted to mention this another point also, C double bond O and C single bond C, that is actually greater than C single bond O, C double bond C. Actually this, it's actually weaker, and this is more stronger. That is what I just bring it to you, this point. C double bond O, carbonyl group, that is C double bond O, it's more stronger than C double bond C. Right, I hope you got the clarity. So keto form, it's more stable. than enol form due to stronger C double bond O compared to C double bond C. And one more point, higher bond energy, thermodynamically more stable. I hope you got the clarity. Keto group is more stronger than enol form. Why? Due to the increased conjugation. That is very important point. Increased conjugation. And other points, and I'm bringing to your notice, aromaticity, resonance, intramolecular hydrogen bonding, and the active methylene group. These are all favors keto, enol, tautomerization. Today, whatever we have learned from 121 to 130, these are the main points they are bringing to you to get the confidence about the related questions. And even suppose some other question comes also, you are able to solve because you got the confident. I hope you got the confident all these points. Yes, and thank you for watching. You just ask what, who, where, when, how, why. Definitely, you will get that idea to solve the problem, whatever problem it may be, whether it is a life problem or questions from JE problems. You are able to analyze when you are having the confidence in you. And thank you for watching. Thanks for your great support.